In this lecture we will cover time cost trade off again. We will look at some different aspects, and we will first review what we had done last time. We will use an example so that the process of how we go about time cost trade off is kind of reinforced. We will look at a tabulation approach. Okay, so this is a systematic way of doing this. We will look at how we can use a tabulation to systematize it, and then we will look at other influences such as bonus and penalty and how it can affect the time cost trade off and especially overall project cost. So if you recall, this was a problem that was given last time. We will just go through this problem. We will first solve it by hand because we will be able to review the process through that. Now if we go into the next level, which is, if you recall, the process of time cost trade off was to be able to, the various steps if you remember. Okay, first we had to identify activities on critical path, okay, and then compare the unit cost of crashing for the different combinations of activities on critical path, and then select the combination with minimum cost, and in case of ties, which in case of a tie activity, select the one which influences the path more, and then reduce the duration. Then you have to redo the network analysis and then go back to the step 1 as we had as it specified here. So if we take this problem, the first step is to actually go ahead and calculate the cost slopes. So you may recall that we calculated the cost slopes. Do you remember what the cost slope was? No, what is the cost slope?
No, crash cost minus normal cost.
Right.
Normal duration minus crash duration.
Right. So we are looking at the cost per day of crashing. Okay, so that was the slope. So here in this table, you remember, if we go back to the problem that was given, we had given you crash cost, normal cost, crash duration, normal duration. We have added 2 more columns to that. One is a cost slope, and 2 is the maximum amount by which the duration can be reduced. Okay, so these are the 2 columns that have been added. So here we will see a number like 300 is obtained by subtracting 3900 from 3600, and the number of days is only 1. You can reduce it only by 1 day, so that is 300. Okay, so similarly the remaining values have been calculated. Now the value here 44,500 is the total value, total cost of the project if everything is done in normal duration. Okay, so this forms the basis for a crashing process, and we have this as the basic network diagram. So if you follow the precedence relationship that was given there, this is the basic network diagram. Now let us use this as a basis and solve the time cost trade off. So we have A, is that okay? And we have the durations that we have actually written it in the box this time. Okay, we have duration of 7, B has a duration of 5, C has a duration of 9, D 19, E 10, 8, 11, 5 and 7. Okay, we have the values, as you can see, the forward pass and backward pass have been done. And if you can tell me the values as we go so that you are doing the participating in it. So 12, 12 and 21, 12 and 31, 21 and 29, 29, 34, 34, 41. Okay. The backward pass value is also given in the network on the PowerPoint, but I am not going to calculate that here because we can do this with a simple forward pass itself. We will do this and then we will go to the tabular method. Now we can see the critical path A, B, C, F, G, I. Okay. So you can see in the slide here it's shown there are 3 possible paths. You have A, B, C, F, G, I, which is 41 days, A, B, D, I, which is 38 days, or A, B, E, H, I, A, B, E, H, I, which is 40 days, and we see that obviously the 41 days is critical, which means my next step will be to take the activities on this path. Okay. And so if you see I have put the cost of the activities of the crash cost of the activities per day beside, so we can see if I take the activities A, B, C, F, G, I, you can see the various costs 300, 500, 425, 250. G cannot actually be crashed, okay, and I is 200. So we know that we have to select the minimum cost, and yes, minimum and on critical path, and in this case it would be I. Okay. So if we go back to I and we will see by how many days can we actually reduce I? 1 day. Okay. So we will go to I and we will reduce it by the 1 day, we will make I 6, which means this goes to 40. Okay. So that was the process we used. Now we know that also if you go back to the basic where we calculated all the parameters, you can see I can only go up to 6, it cannot go any further. Okay. So I has been crashed to the maximum. So we now once we crashed I, has the critical path changed? Has the critical path changed? See I is now if I go back to the diagram you will be able to see that yes, now I changed. I changed 34 this to 6 and it became 40. Will it change anything else? No, critical path is still the same. Every activity in before I has remained the same. So the critical path leading to I will remain the same. The critical path will only change if I change any of the activities which are on the parallel paths. Okay. For example, if I change B, nothing will change because it is a predecessor to all the other activities. It will all be pulled. Similarly, I is successor to all the activities. Okay. So there will be no change in the critical path. Okay. So right now I we have taken out, and the path is still the same, and we still have this table valid. Okay. So we took I last time. Now with 40 days, what is the activity you would choose? Your choices are A, B, C, F, and remember G cannot be crashed anyway. Okay. So G also cannot be crashed. So we have F is at 250 days, F is at 250 is the amount, and we can crash it by how much? So can I take F straight away to 2 days? No, by 1 day, because if I take F to 2 days, what happens? Yeah, no, before F goes down to 6, by the time F goes down to 7, E and H also becomes critical. So I have to take it by one step first. So I take F to 7, Okay, now this goes to 28. Okay, so what has happened now? Now we find this path also. See, so this is at 33, this is at 33. This E and H have also become critical. So any further crashing requires what? Simultaneously. So my combinations now are A alone, B alone, or yeah, C, E, C, H, F, E, or F, H. Okay. So let me write that down. So now that it's getting a little more involved, I will write it down when we take it to this. So if let's just recollect. Step 1 was what? I by 1 day. Step 2, step 3, we have a choice, either A, B, okay, we have, then we said CE, CH, FE, or FH. Okay, so what are the costs? You can read it from there. A would be 300, CE is 575, FE okay, so we have all these combinations, and obviously A at 300 is the least expensive. How much can we move A by 1 day? So we will move A to 6, and this will impact the whole network. Okay, any change in critical path? No, because it was an activity A that moved, it is predecessor to all of it. Okay, so now we have, and we have actually crashed A also to the max. What are our options now? F and E. Okay, so in the next option it is F and E, so I'll have to move F to 6 and E to 9. Okay, yeah, so if it is F and E there, so F to yes, so now I have reduced, so F has gone down by 2 and E has gone down by 1, so both have crashed to the maximum. Let me calculate the result. 20, so here we go to 26, $37. Okay, so now we have crashed out E and F. What is the only, so if you look at the combination now, what do we have left? We have B. So this is basically for us to recollect the process which we went through. Okay, so you get the idea. Now we have B. Once I take B in, I can take it by how many days? I can take it by 2 days. Again, predecessor to everything, it will come down to 35. okay, and in my step after B I am only left with
CE.
CE.
E is crashed to the maximum,
E is crashed max.
so only CH,
C and H.
okay. Yeah, FH is also gone because F is crashed to the maximum, it will come to CH. So we can do this process and you know the principle on which is based. Now as we do a process like this, you will see that we could put it into a series of diagrams of what we have shown. So here is, we have reached up to here, we have crashed A by 8, we have brought A down to 6 days, and then we just brought E and F down, okay. We can go to the next step, which is to reduce B, okay, and the final step is to reduce C and H, okay. So you can see in this we can go through the series of processes and finally the all 3 paths become critical, okay. Now D has also become critical and there is no further reduction possible because everything has been, the other 2 paths have been crashed to the maximum. So if we were doing this the way we did it in the last class, we would go through these network diagrams, and it is very good to understand the network because that is really the basis on which crashing is done, but sometimes it becomes really messy to be able to do it in this form. So what we have introduced is a tabular approach, but let me show you this tabulation, okay. Here, so here what we have is the various activities of the network, the possible path. So you remember the 3 paths ABC FGI, ABDI, ABEHI, okay, and we will write the cost slopes for each of these and the available crash time, and for each step of reduction we will go through an iteration and we will update it as we go. So let us see, first we enter the basic values. You can see that these are the, this is the amount by which I can reduce the activity, and this is the current path length. So for example, D does not participate in the ABCFGI activity, and F does not participate in this activity, H does not participate in this path. So take a look at the table and ask me if you have any questions. So 1 indicates that that activity takes place, is participating in the path, okay. The cost slope you are familiar with it, okay, that is the 300, the 500, all of that you are familiar with. The available time is the maximum it can crash. The path length is what is given at the bottom, is the length of each path. So our base is that this is the length of each path, and we know that G cannot be crashed any further, so we are putting an X, and this is the total cost of the normal duration activity, okay. So we go to the first step, okay, which was, now you have to still use a network, you have to understand from the network what is happening because you will have to keep path, but basically you have to, it gives you a way to express what you are doing. You have to crash I by 1 day, okay, which means you update what happens here. So you are going ABCFI, now you have crashed I by 1 day, there is no more space left to crash I, okay, and your path is reduced to 40, okay, and this path is reduced to 40, all the paths have reduced by 1, okay, and your cost has increased by 200, gone to 44,700. Okay. Similarly, we did the second step. So this was the this is the stage next, and then we remember we had I crash to the maximum. Then we crashed F, if you recall, by 1 day, and the same process is iteration 2, it went up by 250, and this is the resulting direct cost, okay. Then A by 1 day, okay, and this is the result. Now we can keep track of the cumulative cost, direct cost, as we go through the process. We then crashed F and E by 1 day, okay, and resulted in this, okay, and you can see that changes in as we go through each iteration, the available time in each activity has also been updated. Then we went B by 2 days and the duration went down to 35, and the final was C and H by 1 day, and we end up with this final table. Okay. So it is basically a systematic way of entering the values as you crash when you are doing it in a manual approach, if the network gets complex. I would still recommend using this approach if the network is small and you are able to understand and able to keep track of the numbers as you go through. Okay, any questions on this?
In this one, really, we need the network analysis. Without network, we can go for it.
You can, but as your network, what do you say, as your network critical paths change and things like that, it is also nice to have a visual as to seeing where the critical path is going and how it is going. We will take a class later where we will do all this in a spreadsheet. So you can set up things in such a way that you are being very algorithmic in your fashion and not using a pictorial representation at all. But then you have to be very systematic in how you go about it in the algorithmic fashion. Okay, so what I would say is different people have different preferences. If you want a very structured approach where you are looking at just the tables and the numbers and computing, this would be preferred by some of you. Others who prefer a more visual approach and seeing what happens, might be this would be preferred. But without a doubt, this can get extremely messy and prone to mistakes if the network is large and there is a lot of crashing options. So in which case then the tabulation is preferred. But setting up the table can take quite a bit of time, especially if you are in an exam situation or something like that. Okay. Okay. Now this is what we land up with as the total. So you remember the indirect cost was given at 200 per day. So you can see the we have done this calculation where we are showing the direct cost as it increases through the indirect cost at 200, the total indirect cost, and the total direct plus indirect cost. And you can see from here that there are two areas, two durations at which the cost is minimum. Why is that?
After that, it is increasing.
Yes,
No, no.
I have two durations.
Because the crashing of I, the cost was 200.
Yes.
So if you pay, I mean, if you crash I by 1 day and pay 200, you gain another 200. So
right.
it doesn't
So
make a
it
difference.
cancels off. So that because it was 200 and same as the slope value of this, you landed up with two solutions. So it's not a unique minimum solution. You have two minima in this particular case. Okay. Are there any questions? So this is pretty straightforward, and you can, if we go to the 41 or 40 both give you the same time and same cost, and you will land up with a total cost graph which looks like this. Okay, so for both 40 and 41 the value of total project cost is the same. Now let us take, say, the indirect cost is now 300 per day. Okay, so take a look and say what is the change that would happen?
It's now 39 and 38.
Yeah, so it has gone up to 39 and 38, and again you have two values because
There's compensation.
because one of the slope values of direct cost change happens to coincide with your indirect cost. Okay, so because the value is exactly the same, like you said earlier, what you lose by charging for the direct cost, you gain exactly the same amount, so both days it remains the same. Okay. Now what if the indirect cost was, say, something like 350? It would have a unique,
But between 300 and
between 300 and 4. Okay, because so long as I spent 300 and gained 350, I am gaining. I spent 400 and gained 350, I am losing. Okay, so it would be on that value. Okay, so here we have the same values. Now this is, we have seen this is shifted to as because it is 300. Okay, so you need to get a feel of how the indirect cost influences the overall project cost, and why how the value of the indirect cost and the relationship of the slope of the direct cost value.